Part 3 of Worldwide Effects of Nuclear War. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading by Allyson Hester of Athens, Georgia. Worldwide Effects of Nuclear War. Some Perspectives by the U.S. Arms and Disarmament Agency in 1975. Part 3. Some Conclusions. We have considered the problems of large-scale nuclear war from the standpoint of the countries not under direct attack, and the difficulties they might encounter in post-war recovery. It is true that most of the horror and tragedy of nuclear war would be visited on the populations subject to direct attack, who would doubtless have to cope with extreme and perhaps insuperable obstacles in seeking to reestablish their own societies. It is no less apparent, however, that other nations, including those remote from the combat, could suffer heavily because of damage to the global environment. Finally, at least brief mention should be made of the global effects resulting from disruption of economic activities and communications. Since 1970, an increasing fraction of the human race has been losing the battle for self-sufficiency in food and must rely on heavy imports. A major disruption of agriculture and transportation in the grain exporting and manufacturing countries could thus prove disastrous to countries importing food, farm machinery, and fertilizers, especially those which are already struggling with the threat of widespread starvation. Moreover, virtually every economic area, from food and medicines to fuel and growth engendering industries, the less developed countries would find they could not rely on the undamaged remainder of the developed world for trade essentials. In the wake of a nuclear war, the industrial powers directly involved would themselves have to compete for resources with those countries that today are described as less developed. Similarly, the disruption of international communications, satellites, cables, and even high-frequency radio links could be a major obstacle to international recovery efforts. In attempting to project the after-effects of a major nuclear war, we have considered separately the various kinds of damage that could occur. It is also quite possible, however, that interactions might take place among these effects, so that one type of damage would couple with another to produce new and unexpected hazards. For example, we can assess individually the consequences of heavy worldwide radiation fallout and increased solar ultraviolet, but we do not know whether the two acting together might significantly increase human, animal, or plant susceptibility to disease. We can conclude that massive dust injection into the stratosphere, even greater in scale than Krakatoa, is unlikely by itself to produce significant climatic and environmental change, but we cannot rule out interactions with other phenomena such as ozone depletion, which might produce utterly unexpected results. We have come to realize that nuclear weapons can be as unpredictable as they are deadly in their effects. Despite some 30 years of development and study, there is still much that we do not know. This is particularly true when we consider the global effects of a large-scale nuclear war. Note 1. Nuclear weapons yield. The most widely used standard for measuring the power of nuclear weapons is yield, expressed as the quantity of chemical explosive, TNT, that would produce the same energy release. The first atomic weapon, which leveled Hiroshima in 1945, had a yield of 13 kilotons. That is, the explosive power of 13,000 tons of TNT. Footnote: the largest conventional bomb dropped in World War II contained about 10 tons of TNT. End of footnote. Since Hiroshima, the yields or explosive power of nuclear weapons have vastly increased. The world's largest nuclear detonation, set off in 1962 by the Soviet Union, had a yield of 58 megatons, equivalent to 58 million tons of TNT. A modern ballistic missile may carry warhead yields up to 20 or more megatons. Even the most violent wars of recent history have been relatively limited in terms of the total destructive power of the non-nuclear weapons used. A single aircraft or a ballistic missile today can carry a nuclear explosive force surpassing that of all the non-nuclear bombs used in recent wars. The number of nuclear bombs and missiles the superpowers now possess runs into the thousands. Note 2. Nuclear weapons design. Nuclear weapons depend on two fundamentally different types of nuclear reactions, each of which releases energy. Fission, which involves the splitting of heavy elements, e.g. uranium, and fusion, which involves the combining of light elements, e.g. hydrogen. Fission requires that a minimum amount of material, or critical mass, be brought together in contact for the nuclear explosion to take place. The more efficient fission weapons tend to fall in the yield range of tens of kilotons. Higher explosive yields become increasingly complex and impractical. Nuclear fusion permits the design of weapons of virtually limitless power. In fusion, according to nuclear theory, when the nuclei of light atoms like hydrogen are joined, the mass of the fused nucleus is lighter than the two original nuclei. The loss is expressed as energy. By the 1930s, physicists had concluded that this was the process which powered the sun and stars, but the nuclear fusion process remained only of theoretical interest until it was discovered that an atomic fission bomb might be used as a trigger to produce, within 1 or 2 millionths of a second, the intense pressure and temperature necessary to set off the fusion reaction. Fusion permits the design of weapons of almost limitless power, using materials that are far less costly. Note 3. Radioactivity. Most familiar natural elements like hydrogen, oxygen, gold, and lead are stable and enduring unless acted upon by outside forces, but almost all elements can exist in unstable forms. The nuclei of these unstable isotopes, as they are called, are uncomfortable with the particular mixture of nuclear particles comprising them, and they decrease this internal stress through the process of radioactive decay. The three basic modes of radioactive decay are the emission of alpha, beta, and gamma radiation. Alpha. Unstable nuclei frequently emit alpha particles, actually helium nuclei consisting of 2 protons and 2 neutrons. By far the most massive of the decay particles, it is also the slowest, rarely exceeding 1/10 the velocity of light. As a result, its penetrating power is weak, and it can usually be stopped by a piece of paper. But if alpha emitters like plutonium are incorporated in the body, they pose a serious cancer threat. Beta. Another form of radioactive decay is the emission of beta particles, or electron. The beta particle has only about 1/7000th the mass of the alpha particle, but its velocity is much greater, as much as 8/10 the velocity of light. As a result, beta particles can penetrate far more deeply into bodily tissue, and external doses of beta radiation represent a significantly greater threat than the slower, heavier alpha particles. Beta-emitting isotopes are as harmful as alpha emitters if taken up by the body. Gamma. In some decay processes, the emission is a photon having no mass at all and traveling at the speed of light. Radio waves, visible light, radiant heat, and X-rays are all photons, differing only in the energy level each carries. The gamma ray is similar to the X-ray photon, but far more penetrating. It can traverse several inches of concrete. It is capable of doing great damage to the body. Common to all three types of nuclear decay radiation is their ability to ionize, i.e., unbalance electrically, the neutral atoms through which they pass, that is, give them a net electrical charge. The alpha particle, carrying a positive electrical charge, pulls electrons from the atoms through which it passes, while negatively charged beta particles can push electrons out of neutral atoms. If energetic betas pass sufficiently close to atomic nuclei, they can produce X-rays which themselves can ionize additional neutral atoms. Massless but energetic gamma rays can knock electrons out of neutral atoms in the same fashion as X-rays, leaving them ionized. A single particle of radiation can ionize hundreds of neutral atoms in the tissue in multiple collisions before all its energy is absorbed. This disrupts the chemical bonds for critically important cell structures like the cytoplasm, which carries the cell's genetic blueprints, and also produces chemical constituents which can cause as much damage as the original ionizing radiation. For convenience, a unit of radiation dose called the rad has been adopted. It measures the amount of ionization produced per unit volume by the particles from radioactive decay. Note 4. Nuclear half-life. The concept of half-life is basic to an understanding of radioactive decay of unstable nuclei. Unlike physical systems, bacteria, animals, men, and stars, unstable isotopes do not individually have a predictable lifespan. There is no way of forecasting when a single unstable nucleus will decay. Nevertheless, it is possible to get around the random behavior of an individual nucleus by dealing statistically with large numbers of nuclei of a particular radioactive isotope. In the case of thorium-232, for example, radioactive decay proceeds so slowly that 14 billion years must elapse before one half of an initial quantity decayed to a more stable configuration. Thus, the half-life of this isotope is 14 billion years. After the elapse of the second half-life, another 14 billion years, only 1/4 of the original quantity of thorium-232 would remain, 1/8 after the third half-life, and so on. Most man-made radioactive isotopes have much shorter half-lives, ranging from seconds or days up to thousands of years. Plutonium-239, a man-made isotope, has a half-life of 24,000 years. For the most common uranium isotope, U-238, the half-life is 4.5 billion years, about the age of the solar system. The much scarcer fissionable isotope of uranium, U-235, has a half-life of 700 million years, indicating that its present abundance is only about 1% of the amount present when the solar system was born. Note 5. Oxygen, ozone, and ultraviolet radiation. Oxygen, vital to breathing creatures, constitutes about 1/5 of the Earth's atmosphere. It occasionally occurs as a single atom in the atmosphere at high temperature, but it usually combines with a second oxygen atom to form molecular oxygen. The oxygen in the air we breathe consists primarily of this stable form. Oxygen has also a third chemical form in which 3 oxygen atoms are bound together in a single molecule, O3, called ozone. Though less stable and far more rare than O2, and principally confined to upper levels of the stratosphere, both molecular oxygen and ozone play a vital role in shielding the Earth from harmful components of solar radiation. Most harmful radiation is in the ultraviolet region of the solar spectrum, invisible to the eye at short wavelengths under 3,000 angstrom. An angstrom unit, A, is an exceedingly short unit of length, 10 billionths of a centimeter, or about 4 billionths of an inch. Unlike X-rays, ultraviolet photons are not hard enough to ionize atoms, but pack enough energy to break down the chemical bonds of molecules in living cells and produce a variety of biological and genetic abnormalities, including tumors and cancers. Fortunately, because of the Earth's atmosphere, only a trace of this dangerous ultraviolet radiation actually reaches the Earth. By the time sunlight reaches the top of the stratosphere, at about 30 miles altitude, almost all the radiation shorter than 1,900 angstrom has been absorbed by molecules of nitrogen and oxygen. Within the stratosphere itself, molecular oxygen (O2) absorbs the longer wavelengths of ultraviolet, up to 2,420 angstrom, and ozone (O3) is formed as a result of this absorption process. It is this ozone, then, which absorbs almost all of the remaining ultraviolet wavelengths up to about 3,000 angstrom, so that almost all of the dangerous solar radiation is cut off before it reaches the Earth's surface. End of part 3 and end of worldwide effects of nuclear war. This has been a LibriVox recording read by Allyson Hester in April 2008.